So, what I want to talk about today, I'm going to start talking about another Haskell feature that I guess you all have seen along the way, kind of in passing, but we haven't really talked about it. So that's the idea of type classes. So, and here's the the problem that type classes solve. So we know that we have a polymorphic function, a function that has some type variables in the type. It has to work in exactly the same way for any type that you put in here. Right? So, polymorphic functions have to work exactly the same way, or just to say they have to work uniformly for any type. For example, the length function, right? It does exactly the same thing for any list type, right? We've seen this before, and this is why, if you see a type that has type variables in it, that tells you a lot about what that function can possibly do because it's pretty constrained. It can't say, well, if you give me a list of ints, then I'm going to do one thing. If you give me a list of char, I'm going to do something else, right? It has to work no matter what. Okay, but, I mean, that's great in many cases. Like, that's really what length should be, because length really doesn't care. But sometimes we want functions that can work at multiple types, but actually do different things for different types. A good example is the equals function. But sometimes we want functions that really can act differently, act different types. Equals. Right, so equals, we can call it on many different types. You can ask if two jars are equal, you can ask if two ints are equal, you can ask if two lists are equal. But the way that it works is going to have to be different for each different type because there's no kind of one generic way that you can just say, are these two things the same? Or like even plus. So plus in Haskell works on many different types, right? Ints, doubles. But fundamentally the way that works under the hood has to be different for each different type because it has to say, well, I'm going to do whatever you do to add ints, or I'm going to do adding doubles. They're going to be different. They're going to use like different machine instructions or something. So how does this work? How do we do this? And the answer is with type classes. How do we get this in a principled way? Right, so one way you can imagine doing this, like if it was only equals and plus that you wanted to behave like this, you could just build them into the language. And just say, well, equals and plus are special, and you can't make your own things like this. It's just equals and plus will work, And actually there was a precursor language to Haskell called Miranda that Haskell got a lot of ideas from. That's basically what Miranda did. Like equals in Miranda was completely built in, it was special. But that meant, number one, there were some cases where equals behaved a little weirdly, like if the type system said it was okay, but it would kind of crash at runtime or do something weird. It also meant that you couldn't make your own new types and then say how equals worked on your new type because it wasn't built in. And so this is actually one of the things that, just as an interesting historical aside, when people that got together to design Haskell, right? Basically, lots of people were doing research on kind of purely functional, strongly typed languages, and well, when I say lots, I mean like more than 3. But like everyone had their own little toy language that they made to like play around with these ideas. And so a bunch of people said, this is silly. We can't. It's hard to communicate with each other because we don't have any kind of language that everyone uses. So let's get together. There's a lot of ideas in there. Let's get together and like put all the best ideas together to make one language that we can all contribute to. So literally, it was a committee of people that got together and designed the language Haskell, which I'm going further into a historical aside, but why not? Kind of unique for programming languages, actually. Like most programming languages that if you just think about any programming language that you know, typically they're designed by like one or maybe two people, and then who did a bunch of work and kind of set the vision, and then a lot of other people came and worked on it later, but there was kind of like one or two people that just like had the idea and got it started. So like, with Python, it was Guido van Rossum, with the guy Matsuda, something, that made Ruby, C, similar story for a lot of languages. Haskell is kind of unique, probably not like the only one, but the only one that I know of that was designed by a committee. And usually things that are designed by committees turn out terrible. But for whatever reason, they actually did a pretty good job. And it's stuck around. As you can imagine, a committee, like, everyone wants to add their little thing onto the language, and it just like is this monstrosity, and like no one uses it, and it just dies. Somehow that didn't happen. So, one of the reasons I think that it was successful is that they tried to be very conservative. They said, we're not out here to like add tons of cool pet features to this language. We're going to take stuff that's well tested and well understood from other things, and we'll put them together. Type classes was the one exception. So, pretty sure it was Phil Wadler, a guy named Phil Wadler, who had the idea for these things called type classes, to just kind of solve this problem like that Miranda had with equals. The way that equals worked was a little unsatisfactory. And he said, hey, here's this generic mechanism that will solve all these problems and maybe have some other nice benefits. Even though it had, and he kind of showed how it worked, and everyone was like, okay, yeah, sure, let's go for it. And it turned out to be a great choice, because type classes have turned out to be, have had far-reaching influence. They're very practically useful, and they've influenced a lot of other. All right, so enough history. Let's see how we use them. So the way you make a type class, so I'll just write down, here is the type class for I'll call it, probably if I try to load this, it's going to yell at me because I'm like redefining something that's already, I wonder if I can just say, well, but you know what? No, that's bad, because we're not going to get all the. I'll just put it in a comment. So this is basically how. Well, this is how we define a type class. This says we're defining a type class called EQ, and A can stand for any type. So we're saying if you want your type A to be a member of this EQ class, right? So think of a class as kind of like a set of types that implement this class. If you want your type A to be a member of this class, then it has to have a function. It has to have an implementation of a function with this type. So if I make my new type called T, and I want it to be an instance of this class, then I have to define a function equals that has type T to T to bool. And then every time that anyone uses equals, it figures out what type it is, and then it looks up the correct implementation based on the type. So any type A which wants to be an instance of the Q must implement. Okay. So it's kind of like an interface in Java. There's a few big differences. One big difference is that in Java, if you want to have a class that implements an instance, you have to declare that at the place where you define the class. Haskell, you can add instances for a type, in some other module. It doesn't have to be at the time that you make the type. The other big difference is that, like this type A can be an input to this function, it could be an output. You can't, in Java, you can't have methods that like output the type that you're making an instance for. But, well, maybe you can, but you can't use that to, forget it. There's some restrictions in Java that Haskell doesn't. And the way that we would, if we made our, let's say we make our own type, I'll call it T. Where C for constructor. And I can say, to make a type an instance of a class, I just say instance. Instance EQ T, where. And now, well, it's going to, at the moment, it's yelling at me because it's saying, well, it doesn't list the rest of the error, but it's saying, hey, you haven't implemented equals, which you're supposed to implement. So I have to implement something of type T arrow bool. Right? And I'm going to do that by saying, well, if I have a C, well, these are equal if n1 equals n2 and C2 and C2. Oh, did I write? What did I wrote C2 twice? Oh, thank you. And once. So if I have C2s, then they're going to be equal if all of those lists of child T's are equal. And actually, in this case, I can just say T1 equals T2. Well, I'll talk in a second about what's happening here, because it's kind of interesting. Oh, and then I want to say, in either case, for example, how we implement this doesn't really matter. It's not the point. The point is just I gave some implementation for this required thing, and now that means that I can now use the equals function, any place I want on my type T. And if let's look at the type of equals. Because the type, so this says that the type of equals is, A to bool. But that's going to be the type for any particular type A. But if we just ask what the type of equals is, it can't just say A to bool, right? Because that would mean it has to work the same way for any type A, and we know that that doesn't make sense. So what does it actually say? So maybe you've seen this before, right, in types that we looked at. So this double arrow, so, I mean, it does have type A to bool, but then there's this constraint here. Okay, so the thing to the left, to the right of a double arrow is the type, and then the thing to the left of the double arrow is some constraints. And this constraint just says, basically this says this works for any type A, as long as A is an instance of the EQ type class. Okay. And in particular, it doesn't have to work in exactly the same way for every type A, because it can kind of, for whatever type A you choose, it can kind of look up and see, well, how is the EQ class implemented for this A? And I'll use that implementation. And we can also do things like, if I say, int, I can say, or no, let's say I take two A's, I'll say f x, y. If x equals y, then I'm going to return 3, otherwise I'm going to return 4, right? But it's yelling at me, right? Why do you think this definition of f is not allowed? type that I wrote for f is promising that this will work no matter what a is, and it'll work in exactly the same way. But then I tried to use the equals equals operator here, and that will only work for types that are an instance of EQ. So the error says, yeah, there's no instance for EQA. Like you're trying to use equals, but I don't know that A. So I can fix that. I could say, well, one way I could fix it is I could just say, well, I'll just make this function for some specific type that we know, we can call it a test on. But maybe I actually want it to be generic, but I can do that. I can say this. I say, okay, well, this works for any type A as long as it's an instance of EQ. And then when it gets here and we call equals equals, it says, oh, that's fine, because I know that you can only call this for some type A that's an instance of EQ, and in that case, I'll be able to look up and see what the right way is to do equals for that type. So, I mean, this still does give us some guarantees, right? We still know that this is going to work for any type, as long as it's an instance of EQ. And also, the only way we can distinguish between, normally without this, it has to work exactly the same way for any type A. With this, well, it still has to work mostly the same type for any A, except for the fact that we can use equality, and that will work differently depending on the type A. But other than that, we can't do anything else different for different types of A. Yeah.
Is it possible to make a function that works for two different types of instances?
What do you mean? You mean,
Like if you have, instead of A to int, like A to B to int, and B is an instance of something else.
oh, sure. Yeah, of course. I mean, as long as you're only using, the fact that those, like if you say, F says, it takes an EQ. If A is EQ, this is how you write. If you have multiple constraints, you can put them in parentheses with commas. We haven't, well, we can just say like, I'm still going to take two A's just because I can't really make use of the EQ otherwise. I guess I could ask if some A would equal to itself, but that's kind of hard. Maybe I'll say, if x equals y, then I'm going to return z squared. Otherwise, I'm going to return, just the, I have to call it. Right, so this works fine because I'm making use of the fact that I can call the equals operator on x and y because they have this type A, and I'm saying that that has to be an instance of EQ. But then B has to be an instance of num, and we haven't seen what that is, but that's what lets us do things like times or plus. So, B could be int, double, float, rational. So whatever it is, we know that it'll support multiplication, so we can do z times z. And that'll be okay. Does that answer your question? Is that what you're asking? Yeah. I can't like what I couldn't do, for example, I couldn't say, oh, I'll take an A and a B, and as long as they're both instances of EQ, then I'll ask if they're equal to each other. Because the EQ class says, oh, I can take two things of the same type and ask if they're equal, but I couldn't take two different things. Wouldn't make sense, but. Good, other questions? Yeah, Jack.
So that way, would it not work if you were to compare like a string and the number? Like you had a string one and a number one?
Right, no. The EQ class doesn't let you do that, right? It specifically says you have to give two things of the same type. If you wanted to make your own class that said like you could compare two different things, you could do that. So you can actually, there's a way to make classes that have more than one type argument. So you can say, oh, these two types together are an instance of this class, and maybe it gives you a function that says, I can compare the things of these two different types. And as long as you made an instance for, string and int or whatever, then you can do that. But yeah, EQ itself would not let you do that. Yeah.
I guess in like Haskell, like where everything is defined, are there instances for EQ for every like built-in type, and then for num and I guess other?
Yes. So here is so here is the documentation for EQ. So has some laws that it has to satisfy. Actually, it defines both equals and not equals. And basically, you only have to define one of them, and the other one will get a default implementation, just as not the other one. And actually, this just recently got removed, because there was really no reason to have this in here. It's just confusing, because if you implement both of them, it could be inconsistent or something. Whatever, don't worry about that. But yeah, so then here is a list of all the instances that are defined in the standard library, right? So there's a lot of types. Basically, yeah, pretty much every single type that's in the standard library is going to have instance for EQ. So here's int. So like, there's lots of things that you're just like, what even is that? Like, these are like internal types in the GHC or who knows, right? It doesn't. But here's like, yeah, bool, char, integer, big nat, double int word. This is interesting. So this says, find one that's a little more understandable. Oh, well, so here's a great one, right? This one says, a list of A, that is an instance of EQ as long as A is, which makes sense, right? We can compare two lists to see if they're equal as long as we know how to compare the elements to see if they're equal, right? And the implementation of this, and we'll do an example of this in a minute, but the implementation of the equals operator for lists would end up calling the equals operator on the elements, right? It would say, oh, are the first two things equal? Yes, no. So this is how you can say that. You can kind of have instances depend on other instances, right? Or like, either A, B, you can compare those for equality as long as you can compare A's for equality and B's for equality, right? But yeah, pretty much every, even like, oh gosh, like 6 tuples, it can be. Why you would ever want to use 6 tuples, I don't know, but it's there. I guess it goes up to 15 tuples. Yeah. So yes, to answer your question, absolutely. And yeah, but then if you make your own type, you can make an instance of these. One thing I will mention here at this point is that actually, for EQ in particular, there's certain type classes that GHC knows how to generate code automatically. Because like, the code for this, it's pretty straightforward. You could kind of like derive this automatically, just by looking at the definition. So you can actually say, we've done this deriving before, like for deriving show, right? But you can say deriving EQ. And now it knows how to compare. It basically, GHC will like write this code for you. It just like recursively calls equals on all of the components. But that only works for specific things like EQ. All right. Any other questions? I'm going to do an example of writing our own type class and making some instances for it, just to kind of see a little more detail how it works. So, I'm going to make a type class called call it listish. We'll call it well, I'm going to call it So basically, the listish class is for things that can be converted into a list of ints somehow. And we get to decide what that means, right? So let's make some instances. So we can make up whatever we want here. So like, well, how about, okay, let's start with like, actually, let's just do int. Okay, so this means now I have to give a function that takes an int and gives a list of int. So it will just say this function that takes an int and just gives a singleton list containing that element. Okay. I could say like instance listish char where listish c is, well, we could just say like the list containing or it gives you the, we have to import data.char. Or it turns a char into its Unicode code point, so it's just like what number code is that character. But I want to do one. So that if we have a list of things, we can turn that into a list of int, as long as we know how to turn A's into list of int. So, alright, so this says list A can be turned into, as long as we know how to turn A into. Okay, makes sense? So, I guess the obvious way to do this is if I have to write a function that takes a list of A and turns it into a list of int, right? And I know I have a listish instance for A, so I know that I can turn A into list of int. And if I do that for every A in this list, I'll get a list of lists of ints. And then I could just call concat to turn that into a single list. Right? So I could say listish A's is concat of map listish A's. I could also just have said listish equals concat of map listish. And actually, doing map and then concat right afterwards is so common that there's even a function for it. So I could just say concat map. Now there's something a little strange about this, or I mean it might appear strange, is that if you just look at this, it looks recursive, right? It looks like we're defining listish in terms of itself. It's not. It's not recursive. So this listish here is defining what the listish function does for lists of A, but then we're calling this one on values of type A. So when I'm doing this, it's calling some other implementation of listish, for whatever the type A is. So it's not actually calling itself because it's not calling the same, one for the same type. Right? Because listish isn't just a single function. It's like a collection of functions, one for each possible type that we could use this on. And Haskell, we don't have to tell it which one to use. It just is doing type inference, and it's figuring out, oh, since this one you're calling it on a value of type A, then you must want some other instance. Let's just try this out. I'll change the name of the file later. if I say like listish 3, oh, I see. I have to say something like 3 int. And, okay, the problem is when I just say listish 3, well, what type is 3? Actually, this is an interesting aside. And maybe I've avoided talking about this just to not confuse you before, but now we can talk about it. So just like, what is the type of 3? You might think it's like an int or something. But it's not, because actually 3 we can use it as a double, we can use it as an int, we can use it as an integer. So even numbers themselves can have these multiple types, right? So this is the type of 3. 3 says, oh, it can have any type you want as long as it's an instance of num. So the num class, oh gosh. So in particular, one of the things that num says you have to provide is a way to turn an integer into your type A. And so basically when you type 3, it's kind of implicitly wrapping it in a call to this from integer thing. So whatever type you want to use it at, 3 is literally an integer, and then we'll just call from integer on that to turn it into whatever other type you're trying to use it at. So maybe double or int or whatever. And then, just as an aside, we can see the other things that num says you have to provide. It's a little controversial, perhaps, because there's kind of a lot of stuff squished into this one class, and maybe there's better ways that maybe to organize it a little more granularly that would kind of be more algebraically sensible. Like, because, for example, sometimes there's things where it makes sense to define plus and it makes sense to define times, but there's no sensible way to define minus. And you can't use, or you kind of have, you can use num, but you just have to like make minus be an error or something. Whatever. But basically it says like, it could be plus, times, minus, you can negate things, absolute value. Signum is like what the sign is. Okay. So that's why when I said listish 3, it gave me some giant error. It says, oh, this type was ambiguous, because it doesn't know what type 3 is supposed to have, because it could have any numeric type. And then also listish can take any type you want, as long as it's an instance of listish. And so between the two of those things, it didn't know what type we wanted 3 to have. It has no way to figure it out, because 3 doesn't inherently have a specific type. Listish doesn't inherently require a specific type. So, it's like, I don't know. And it matters, because what type it is might depend on, or will influence how listish works, right? Because listish can work in different ways depending on type. So one way to fix that is just to like say, no, really, I want 3 to be an int. And it's like, oh, okay. I can say 3, 4, 5. So it ends up just being kind of the identity for lists of int, because it's calling listish on each individual int, which is getting turned into something like this. So we have a list of like singleton 3, singleton list 4, singleton list 5, and then it does concat. And it just turns it into one list. But we should also be able to do things like so like if I do a single character X, right, it just gives me its ASCII code. But I should also be able to do something like hello, because a string is really just a list of char. So I get a list of all, and I can even do hello. That works too. It actually used this instance twice, right? First it said, oh, you have a list of char, no problem. I'll use this, because I know how to do list of char, so I'll call listish on each list of char, and then do concat. And then said, oh, how do you list of char? Well, I'll use this again. I know how to do a char, so I'll do that, and then so we could, we could nest these as long as we want, and it would still just keep. can we come up with a reasonable way to implement this? So this is, if you give me a pair of an A and a B, then I can turn that into a list of int, as long as we know how to turn A's into a list of int, and also how to turn B's into a list of int. I guess we can just call listish on the A and call it on the B, and we'll get two lists of int, and we can just like plus them together. Seems reasonable. We could do other crazier things, I guess, but listish AB, or I'll call it is listish X. Oh. Yep. I mean, turning things into a list of ints is not a particularly useful thing, but turning things into a list of chars, on the other hand, like a string, could be interesting. And that's actually exactly what the show class is, right? It has a way to turn kind of arbitrary, or certain types into a string, so you can print them out. What are instances? Here's the actual definition of the class. Some of this, don't worry about this. Don't worry about this. Show is correct. But that's the main thing that it provides, right? Is just a way to turn an A into a string. Let's see. One other type class I will show you that's in the standard library is ORD. It's right here, I think, actually. Yeah, so totally ordered data types means the values in your type can be put in a specific order, like from smallest to biggest. So it actually has a bunch of methods. So there's this compare thing that returns an ordering. The ordering basically says, is it less than, equal, or greater than? So if you want to get those three cases in one go, you can call it compare. And then obviously less than or equal to, greater than or equal to, max and min. Because max and min you can implement by default by saying, if this is less than this, then that else. And again, there's tons of instances for ORD. So, and again, GHC can automatically, if you say deriving ORD, it can generate code for you. But notice that it says, yeah. So basically, this is saying anything that's going to be ORD has to also be an instance of EQ. So you can't have a type that's an instance of ORD but not EQ. Kind of that makes sense because if you can compare things, you could ask if is this less than or equal to this, and is this less, or is X less than or equal to Y, and is Y less than or equal to X? And that would mean if both are true, then they have to be equal. So you could use ORD to figure out if they're equal anyway. So you might as well require. And I think that's one of the laws. It's if you make an instance of this, Haskell doesn't check that these laws are true. But Haskell programmers will be mad at you if you make an instance where these things aren't true. Because Haskell programmers care a lot about algebraic laws and being able to reason about their programs. And if these kind of nice laws don't hold, then it's harder to reason about what things are doing. Cool. Any other questions at this point? type class that I'm going to tell you about, that's defined in the standard library. But we're going to spend, I'll introduce it today, and then we'll spend probably all Wednesday just talking about this type class. And this is Monoid type class. So what is a monoid? So the word monoid comes from math, I guess. So this Haskell type class really just is saying types that have a certain kind of mathematical structure to it. Okay, so a monoid is a type, we'll call it M. Which supports two operations. So there's one called, for historical reasons, it's called M-append, but there's a synonym for it, which is just this operator that looks like that. So I'm going to use this operator pretty much all the time because it looks much nicer than writing M-append everywhere, but if you actually define an instance for this monoid class in Haskell, you have to say M-append. Is an associative binary operator. That means, well, I'll say it has type So it has type M to M to M. That means it takes two things of type M and gives you one thing of type M. So, it's a way of combining values of type M. Okay, so that's what I mean when I say it's a binary operator. When I say it's associative, you might already know what this means, right? When you say, oh, what does it mean that plus is associative or plus plus is associative or whatever. It just means that, if you've looked at the, well, I don't think associativity is one of the properties that you wrote down in the AGDO module book. Right, it just means if I combine three things using this combining operation, it doesn't matter in what order I do it. If I do these two first and then combine the result with X, it's the same as if I had first done this two. It means it doesn't matter how I parenthesize it, right? The order might matter, so it's not necessarily true that combining X with Y doesn't have to be the same as combining Y with X. But the order of the parentheses, or where I put the parentheses. So i.e. parentheses don't matter. Okay, and then there's one other thing called M-empty, which just is a type M, which is an identity for this operator. That is, if I do X, combine X with M-empty, that's the same as X, which is also equal to okay, so it's a binary operator that is associative and that has an identity element. There's some element that when I combine it with anything, it doesn't change the thing, I just get that thing back. So, I don't want to talk yet about the actual Haskell syntax for this. I'm just thinking about it kind of in a mathematical sense. Can anyone think of an example that you might know of? What's some operation, a binary operation that has these properties? Like it's associative and it has some identity element. You for sure know of several, although maybe you haven't thought of it in these terms. Yeah, so this operation is addition on like, say, integers. And then what's the MMP? Exactly, yeah, good. So, one example is, integers. This is, say, finding operation is addition, and okay. Yep. What else? Well, first of all, does everyone believe this one? Does this make sense? So definitely 0 is an identity for addition, right? 0 plus anything, just, 0 plus x is x. And also addition is associative, right? A plus B plus C, doesn't matter how I put the parentheses. Actually, addition is also a commutative. That means we can switch the order, that doesn't matter. That's not required for a monoid, but some monoids do have that property. Anyone think of another example? Jack?
Put a plus plus for let's.
Yeah, good. So lists, combining operation is plus plus. And what's the identity element, Jack?
Could just be empty list.
Yeah, exactly, right? If I do empty list plus plus some other list, I always just get that other list. And yes, the combining operation is associative. If I say a plus x's plus plus y's plus plus z's, right, where I put the parentheses, doesn't matter. This is a good example because this one is not commutative, right? So if I say x's plus plus y's, that's not the same as y's plus plus x's. I get a different list in the case. But it is still associative, right? The parentheses don't matter, even though the order matters. So, note, this is also slow. This is not. Okay. We're out of time, but we will, we'll do a ton more examples next time. So you can be thinking, if you can think of other examples of this. There are several more that I'm sure you know of, and then some other ones that you probably have